Okay, the next session.
Next session, yes.
There we are. We have three speakers that were lined up for this session: Todd Hylton, Eugene Rui, and Georgi Georgiev, but Eugene had to withdraw. So we're going to assign a half an hour to each of Todd Hylton and Georgi Georgiev if they can fill the time. Are we good with that?
Yes.
Todd Hylton, are you ready to go?
I'm ready to go.
All right.
So I'm going to share my screen. Okay, is that visible to everyone?
Yes.
Yes.
Okay. Get rid of this. Okay, hello everybody. You know, I really regret that we're doing this online because I'm a newcomer to this community, and I would really appreciate having the opportunity to meet you all. So hopefully that happens sometime in the future. I'm at UC San Diego, and I'm going to talk about a model system I've created that I call the thermodynamic neural network. So here's the outline for the talk. I'm going to give a little motivation. I'm going to describe the model qualitatively. I'm not going to give you any equations. If you want to see the equations, you can refer to the paper at the bottom referenced here. And then I'll show you the results in terms of simulations, videos, essentially, of what this network does when it's evolving. So motivation here, wow, okay, I got a problem here. Hang on just a second. All right. It wants to advance itself for some reason. Motivation. Okay, so several years ago, I used to be a DARPA program manager, and I funded some work at UIUC by Alfred Hubler, where he showed this really cool result. This is the same result by another group at Stanford. But what we have here is a petri dish with oil in the bottom, some conducting beads within the oil, a grounded electrode that goes around the outer part of the petri dish, and then a high voltage electrode just over the top of it near the center. And this is what happens when you turn on the voltage. You see this very interesting and spontaneous evolution of organization, presumably because the system is trying to conduct charge between the electrodes, and having the balls form these strands or wires, so to speak, facilitates that. So here's another example from another group of authors where they have a slime mold sample here with food sources surrounding it, and they show how the slime mold grows over time. And much like the case that I just showed you, these very interesting sort of filament-like structures form between the sources of food and the central location of the slime mold, as though it's building highways essentially to transport the nutrients that it needs. And the authors here said that you know, they put the food sources in places of heavy population density within the city of Tokyo, and that the resulting structure that emerged looked a lot like the Tokyo subway map. So my question has been, why can't I build you know, a physical system, or at least a model of one, that may show some similar sorts of ideas? And that's the origin of why I started working on this thermodynamic neural network model. Over a long period of time, I've realized that these were the core ideas that I was incorporating into the model. One was one of conservation, the idea here being that physical systems are built to conserve physical quantities, and they can't vanish, but they can be transported through an open system. Potentiation has to do with the accumulation of these conserved quantities, and that accumulation creates potentials that want to disperse them. Fluctuation, when exposed to finite temperatures, the system can spontaneously sample configuration spaces adjacent to their current state of organization. Dissipation, that these fluctuations should be tied to dissipation via a kind of positive feedback. Adaptation, that this fluctuation and dissipation can also result in adaptation that can both stabilize new structures and destabilize old ones. And equilibration, finally, that all systems are basically trying to find an equilibrium with their environment subject to various internal and external constraints. And so the key hypothesis that I have here is that open physical systems evolve organization via fluctuation, dissipation, and adaptation to efficiently transport conserved quantities, and they do this in order to relieve potentials in their environment. So that's the basic ideas behind the model. I'm going to briefly describe the model qualitatively. It has a lot of things in common with an Ising model, which I'm showing sort of here on the left of the screen, and then the thermodynamic neural network model on the right side of the screen. If you're familiar with the Ising model, as I suspect many of you are, it's a network of nodes where each node has a state, which is commonly thought of as a spin. The nodes are connected to each other through a symmetric, weighted connection, usually described as a weight of some sort. Each node is a kind of single compartment in which the weighted sum of the adjacent spins are used to make a determination about what the spin of this particular node should be, which is this central node here in this diagram. So the TNN model has some things in common with the Ising model. Again, it's a set of symmetric, weighted, of nodes connected by symmetric edges. The edges are weighted. In this case, I'm thinking not about spin being aligning amongst the nodes. I'm thinking about charge being transported across and through the nodes in a kind of network. And this charge is notionally the conserved quantity that I'm worried about maintaining throughout the network. It will turn out, as I'll describe in a moment, that the charges naturally accumulate into 4 different compartments, and the node is essentially a kind of switch that's connecting some of these compartments together. The most natural analogy that I can think of from everyday life is a traffic light. When I come to a traffic light, not all the cars can cross at the same time, so the lights change in order to move the cars. And that's essentially the role of the node here. It's switching in order to move charges across that can't be moved across simultaneously. All right, so the way the charge accumulation works, it turns out there are 4 different compartments, and the compartments are defined both by the sign of the adjacent node states that are connected to the central node. So there are positive and negative potentials, I think of them, and then there are positive and negative weighted edges that connect them. And so there are 4 compartments having to do with these 4 ways of putting these different polarities together. So charge can accumulate in these compartments, and it's only relieved when the node makes a decision to let charge of a particular sort flow through it. And because of the requirements of charge conservation, the 2 compartments form pairs, and so the node is basically deciding to connect 2 pairs or another pair, like the traffic light. The other key point is that the charges are conserved. Positive and negative charges, they attract each other, so they create a path along which the charge should flow, but they never cancel each other, unlike a typical neural network model. All right, now, so that's how the nodes are updated. But what happens is whenever transport happens through the node, the transport is imperfect because there are thermal fluctuations, the weights are never perfect, and so forth. So then what can happen is the edges that contributed to the compartment charges can be updated in such a way that future transport will be improved. Now, in every case, in the selection of the node states and in the update of the weight edges, it's Boltzmann statistics. Basically, you use a local Boltzmann distribution and you update the nodes and then you update the weights. Oh, and the other point here is that while certain compartments are selected and updates to their edges are made, other compartments that are not selected simply accumulate charge and their edges are unchanged during this particular node state selection. So the net of it is that long-term memory is stored in the edges, the edge weights of the network. Intermediate-term memory is stored in charges on the compartments, and these may persist over multiple node state decisions. And short-term memory is essentially the collection of node state energies. So the nodes can be connected in the networks of any type. There are no dynamic instabilities. There are no problems with feedback in this network. Typically, in the examples that I'm going to show you below, I'm going to show a number of nearest neighbor networks because it's very easy to visualize the dynamics in nearest neighbor networks. So here, again, the blue circles are the nodes and the weights are the edges. And so the way the network is updated is, well, before I say that, let me back up for a second. The network, because of these charge conservation requirements and these matching of compartments, it turns out that the nodes sort of want to order antiferromagnetically so that they're alternating positive and negative sign polarities on these nearest neighbor networks. There's some complexity here with sort of the network structure about whether it's bipartite or not, but I'm not going to talk about that now. Now we can take some subset of those nodes though and add an external bias. So you can think of this as, for example, the wires over the Petri dish, in which we can inject charge and therefore bias the network to evolve. So all of the adaptation, as I mentioned before, is done by relaxation using Boltzmann statistics. In the node update methodology, there's basically a Markov chain Monte Carlo that just goes through the nodes one by one, updating each one independently as it goes. The edge weights, it turns out, are only updated when the node thinks that it has found a local equilibrium. In other words, it can look over its energy over some previous time steps and say, hey, am I near the temperature? Are the fluctuations that I'm seeing near the temperature or not? If they're lower than the temperature, then I'm probably in a local equilibrium. And when that's the case, I'm going to update my weights. If I'm not in a local equilibrium, I'm not going to update my weights. I'm simply going to communicate with my neighbors, tell them what I'm thinking, so to speak, and wait for them to change until we find a local equilibrium. So it turns out that in doing this, you can get some interesting network dynamics, which I'll show you. I view it in sort of as being two key pieces. One is a kind of rapid, global, and reversible relaxation of the node states that enables the network to sample fluctuations over multiple scales. In other words, if I'm not making any irreversible changes and I'm sending changes to my neighbors or sending changes to their neighbors, we can all sort of fluctuate until we find a common state that we agree upon before any of us makes an update. Furthermore, I point out, as compared to other neural networks, there are no learning or decay rates, there's no backpropagation, and other than the sort of the setup of the network and the Markov chain Monte Carlo, there's no top-down orchestration, which is so evident in neural network models today. So simulations. I'm going to show you a number of 2D nearest neighbor network results. And so each of these sort of interesting looking frames here is a frame from a video of the evolution of a network. Every square here is intended to represent a single node. White represents a node state of +1, black represents a node state of -1, and the gray is somewhere in between. So in this case, there are 900 nodes. Every one is connected to his 4 nearest neighbors. The node and the edge temperatures are the same. There's no external biasing, so this is a node that's only interacting with the thermal bath. And there are periodic boundary conditions so that this edge connects to this edge, and this edge connects to this edge. And what you see when you just set up this network is you see domains of antiferromagnetic order, which you can see here. And that antiferromagnetic order shifts around in time as the node evolves. So here's exactly the same network. I find it very hard to look at this antiferromagnetic order, so I'm going to display it henceforth as ferromagnetic order by essentially inverting the sign of every other, the sign of the display of the node state in every other node. So now you can see domains that look primarily black and primarily white, and you can easily see domain walls between them. Okay. Now, what happens if I introduce an external node and I bias charge into the network? Well, what happens is the external nodes are able to polarize the regions of the nodes immediately surrounding them. Their polarization depends on their polarity, as well as, it turns out, on the partition. This network is bipartitioned, and it matters which partition the node sits in. That's a technicality that I'm not going to be able to cover today because I simply don't have time. And this is what happens if you put 2 nodes of opposite polarity into a similar kind of network. If you have opposite polarity nodes and an opposite partition, they will form a nice bridge. They will connect. In fact, they'll grow strong weights between them, which you can't see. And that the polarity of that connection will change as the polarity of those nodes change. On the other hand, if they're in the same partition, they will spontaneously, they will polarize the regions around them, and they'll create a sharp domain wall between the 2 of them. And so here's what happens with two nodes that have the same polarity. They can jointly polarize if they're in the same partition, but they can't grow strong weights because there's no charge transport between them. And if they're in the same polarity but in opposite partitions, again, they'll make a kind of weak domain wall. All right. So hopefully that gives you kind of a generic sense of what the network does. Now I'm going to show you several videos of network evolution. So this is the same kind of network. It's a two-dimensional network. It's a much larger number of nodes. Each node is connected to its 16 nearest neighbors in its own partition. The node temperature is higher than the edge temperatures because that ends up giving some interesting dynamics, which I'll show you. There's no external biasing in this particular case, and there's still periodic boundary conditions. So this is what happens when you let the network evolve from an initially random state. Then in this particular case, what you're going to see is the network fairly rapidly converges on a roughly single domain dark state in this case with lots of interesting smaller scale fluctuations going on. So here is exactly the same network at a slightly higher node temperature. And in this case, what happens interestingly is that the network doesn't converge on a single state. It shows interesting sort of multi-scale dynamics over as long a period of time as I can simulate it anyway. I'll skip ahead a little bit so you can, hope I can skip ahead here. Well, for some reason, it's not letting me fast forward, which is going to be a problem. Okay, well, let me back up for a second. So interestingly, so with these networks, you can do things that you would like to do, like look at statistics of the network, like what are the energy of the nodes, what's the average entropy of the node, what's the ordering in the network. And so it's a handy way, I think, to connect ideas that are common in thermodynamics to a detailed model where you can play with the sort of microscopic parameters and see what happens. So this is what happens when there are bias nodes, external biases placed within the network. So this is a node of 10,000. This is a network of 10,000 nodes. Again, it's a bipartition nearest neighbor with 16 connections per node. Same conditions as almost exactly the same as the last two videos that I showed you. In this case, however, there are 10 pairs of bias nodes with opposite polarity in opposite partitions that are changing state with different periods. And so this is what happens when you turn this network on and let it evolve from an initially random state. And so what you're going to see is the bias nodes, which are the green ones. Hopefully you can see these little green specks. Sometimes they turn yellow. I have that to tell me if they're doing something that I don't want them to do. But the idea here is you can see that the nodes polarize and rapidly propagate potentials through the network to connect to other nodes that have other potentials. They also spontaneously form and destroy domain walls very rapidly. And I was going to fast forward this so that it would become more obvious. But what happens is, as the weights grow stronger, there's fewer and fewer of these regions where you have sort of this gray, noisy stuff going on, and you get stronger and stronger connections within the network. The comment that I would make here is that the way I interpret what the network is doing is that the structure that emerges within the network is a kind of representation of the external potentials that are applied to it at any given time. And again, as the network is exposed for longer periods of time to the potentials, it gets better and better at transporting the charge, the losses are lower, and it continuously refines. There are some issues here with geometric frustration. Some of the nodes can't connect to each other because there's this 2D network. Those are all easily circumvented in a randomly connected network, which I'm not going to show you because they're nothing to look at. Let's see, how much time have I got left? Okay, a few more minutes. I'm not sure if I can't fast forward this, if it will make sense, but let me turn it on anyway. What I'm going to do here is I'm going to variously turn the external bias nodes on and off. When they're off, they're red, and when they're on, they're green. And what I wanted to see is after a few cycles of turning on and off, when the external potential was turned off, and I think of this as being the node in kind of a dream state, would it dream things that looked like potentials that it had been exposed to before? So here's the network going on, and this is a very long simulation, and since I can't advance it, I'm not sure I'm going to be able to show you the result. So now it hasn't seen any potentials. It's doing much like what I showed you in the earlier one, where there's sort of this multi-scale dynamics going on. And then, oh, gosh, I wish I could fast forward this. Let me see if I can do that. Let me try this for a second. Okay, so now it's being exposed to external potentials. The bias nodes are green, and it's driving the dynamics of the network. This happens a few times through the course of this simulation. And I want to show you what it looks like when it's dreaming. So now it's dreaming after having been exposed to potentials over a period of time. And it's pretty evident, at least qualitatively, that the dreaming, does look like, has something to do with the organization of the external potentials that it's seen in the past. Okay, let's go back to the full screen. Okay, so the key thing that I want to get across here, and this is still a work in progress, is I think that this model can unify some ideas of conservation, potentiation, fluctuation, dissipation, and adaptation, and equilibration in a common physical model and illustrate a self-organizing, complex, adaptive system. And I think this could be a great tool for many of us to inject our ideas about how we think things organize and see if they actually happen in a simple model. I was also struck by this. A colleague showed me this and said, hey, some of those videos that you showed look a lot like this cosmic microwave background fluctuation plot that I've seen several times, which I think is, I don't know what that means, but I think it's interesting. Lastly, I want to say that I've been spearheading an effort that I call thermodynamic computing to bring some of these ideas to the computing community, where I think they could be of great value, and where, as in many other communities, the ideas of thermodynamics are not entirely well appreciated. There was a report published from a workshop that was held a little more than a year ago. You can look it up online. It's called Thermodynamic Computing. And in it, there's mostly a vision for a future in which thermodynamics is the core concept in computing, and where they do things like organize themselves. And part of the message that I'm bringing to this community is communicated in this simple diagram, where I sort of divide up the world of computing into three domains. There's a quantum domain, a classical domain, and a thermodynamic domain. This is a plot of characteristic length and characteristic time scales, and to give you a sense of that scale, I've essentially set the energy of a free electron to kT at room temperature, and you can see roughly what the sizes are. So in the classical domain, I argue that here we have scale separation. We largely average over the fluctuations at the device level so that they don't matter. This makes the system mechanistic, makes them essentially infinitely scalable in this direction, but you run into problems as you try to make things smaller. This is the thermodynamic domain. In the quantum domain, the systems are coherent, or they aspire to be, and so they are essentially single scale. They have the problem as those systems try to get larger, they also run into this thermodynamic domain.
Todd,
So,
Todd,
yes.
we're down
Yes.
to 4 minutes. There are a
Okay.
couple of questions waiting for you.
Okay, I'll stop. So last comment is, the thermodynamic domain is by far the most interesting one, in my opinion, and the one that would really be a revolution in computing, and I'm trying to take that message forward.
Okay, there's a question from Christian Siegle. Are you there?
I'm here, yes. Trying to get back to the right screen here, okay?
We have another question from Carrie King.
Hi, Garvin. Yeah, thanks, Todd. My question is just, can you explain more of why you think the dream state occurs? Is it because the weights change? I'm not a neural network person, so is it because the weights change and then they're remembered and then follow that pattern?
Yeah, so the way the network is set up so that it essentially tries not to forget things that it doesn't need to forget. And it's not doing sort of a constant statistical sort of update the way most neural networks do. So it does have a way of preserving what it's learned in the past without destroying it. That's you know, I don't know how well it works honestly, but that's the gist of it.
Okay. Christiane, are you ready to put your question now?
Yes, thanks for the presentation. My question is did you perform a fine-tuning of the model, measuring the order parameter to check if there is a phase transition?
Phase transition, I haven't done, I have seen things that look like phase transitions before in other models. It's a very large space of things that can be examined, and I have not done enough work in that domain yet. But for example, in those examples that I showed you, if I were to turn the temperature up or down on the nodes a little more, you would see it go all the way from looks like a crystalline state where there's essentially no fluctuation to a state in which it looks like a gas with only very local order.
Do we have any other questions? We have another minute or two for this session.